One of the things that we're interested in with statistics is trying to estimate population parameters from samples. In general, you do not know what the value of the mean of a distribution is to start with, or what the value of the variance of a distribution is to start with. To get an idea of what those values need to be, or might be, we need to do sampling and estimating from the sample. So that's what we're going to devote a good chunk of the semester to, is talk about how do we get good estimates for population parameters. So in this section, we're going to concentrate on what we call point estimates, and we'll talk a little bit more about that in class. And we want to try to figure out what the best point estimate is for a particular population parameter. So to motivate this a little bit, let's look at this particular example that I set up. If you have calls coming into a call center and you're looking at the number of calls that arrive each minute, we can reasonably suspect that might follow a Poisson distribution, because we think about waiting time until, not waiting time, the number of occurrences of a particular event over a fixed time interval. So if we have calls coming into a call center and count the number of calls that come in, certainly that's a discrete random variable, and certainly we could expect that a Poisson distribution models that situation pretty well. So therefore, we know that the distribution has to have a PDF that looks like the lambda to the x e to the minus lambda over x factorial. That's the PDF of a Poisson distribution. But again, we don't know what lambda is to start with. So we need some way to figure out an estimate for that lambda if we're going to try to make some probability or statistical inferences for this particular scenario. So to do this, let's say we have a random sample again, because that's how we're going to estimate things. We're going to take random samples from the distribution. What's the probability that we actually get these values? Well, this is a discrete situation. So I would plug each of these into the PDF to get the probabilities associated with each of these values. And then, since they're all independent, we can multiply these particular probabilities together to get the probability. So the probability that this random sample actually occurs is just the product of the probabilities for each of the individual observations, which would just be the product of your PDF. And so in this case, we know explicitly what the PDF is, so this is just plugging in x sub I into the PDF for each I. So we've got a product from 1 to n of lambda to the x sub I e to the minus lambda over x sub I factorial. So notice, well, all we've done really is just taken the PDF, plugged in the values that we see from the random sample, and multiply them all together, because they're all and probabilities and they're all independent. So we should be multiplying together to figure out the probabilities. So this actually second to last line here that we did in the above is actually referred to as the likelihood function of lambda. So the likelihood function, so how likely is it that a particular lambda is the value that we're interested in, is the product of all of those probabilities. We want to maximize this function. Given a random sample, what's the maximum likelihood for a particular lambda? So we're going to do calculus things to figure out what the maximum is. All right, so notice that in its current form we get a product, and that would be a nasty product rule in general to try to take. So instead of maximizing the actual function, many times what we'll do is we'll maximize the log of that function, because the natural log, will change products into sums. So we're going to take the natural log, and we'll refer to this as the log likelihood function. So the natural log of the likelihood function is the natural log of the product. Again, natural logs turn products into sums, and then we turn, and not only do we turn products into sums, we turn quotients into differences. So when we take the log of this quotient on the inside, we'll take the log of lambda to the x sub I. We can bring that exponent down in front, so we get the x sub I, the log of lambda. Plus, we would have log of e to the minus lambda, but log of e to the minus lambda is negative lambda. That's why we've got a minus lambda here. and then minus log of x sub I factorial. And there's not a lot we can do with that particular one, except as a log of a product. You could make it a big, long log of a sum if you really wanted to, but we don't have a good notation then for the factorial symbol in that case. So we're not going to do anything with that. So, and in particular, we'll see why here in a second. All right, so this would be the log likelihood function. This is the thing we're going to try to maximize, and the reason why we can maximize the log, and it'll occur at the same place as the original likelihood function, is because the log is an increasing function. It's not going to change the value of the maximum at all. All right, this is definitely much easier to differentiate because now I'm differentiating a sum rather than a product. Notice what happens when we differentiate with respect to lambda, not with respect to x, with respect to lambda here, because we're trying to maximize this with respect to lambda. Derivative of your natural log of lambda is 1 over lambda. The x sub I is a constant as far as that's concerned. Derivative of lambda is just 1. And then this part over here, what I mentioned a minute ago, why we didn't really worry about simplifying it, is that this is now just a constant. Derivative of the constant 0. It has no effect on where the maximum occurs. All right, so we differentiated. This is the derivative. We want to find its maximum. To find maxima, we need to figure out where the critical values are, which means we actually want to take the derivative, set it equal to 0, and solve for lambda. So the derivative was that sum of x sub I over lambda minus 1. Set that equal to 0. Split up the sum over the difference and pull out the 1 over lambda in the front part. We're still trying to solve for lambda here, so move the part that didn't have the lambda to the other side. This sum is easy. That's just equal to n. And then if we rearrange things, we get the lambda is equal to the sum of the x sub i's over n. This is the sample mean. So notice that when we found the critical value here, the critical value was just the sample mean. And that should not be a huge surprise that this would be the maximum likelihood estimator for us, because what is lambda for a Poisson distribution? It is the mean. So this is not a huge surprise that we get that our maximum likelihood estimator for lambda is the mean. We can check pretty quickly. We're talking about this being the maximum likelihood estimator. We better check that this really is a maximum. But if we take the second derivative, remember this left-hand side was the derivative. If we take the second derivative, you're going to get a minus x sub I over lambda squared here. This will go away. That's definitely going to be negative for the value of lambda because we have a minus 1 over lambda squared. So this will be negative, which means the function was concave down, so we really did have a maximum. In general, when you do these maximum likelihood estimator problems, you're going to have a maximum, not a minimum. So usually, we can do a cursory check, but it's going to be what we expect it to be. All right. So we call the statistic, the x bar, the maximum likelihood estimator for lambda. So whatever the statistic is, when we generate random samples, take all those possibilities, that x bar, the distribution of x bar is the maximum likelihood, and with maximum likelihood estimators, we denote it with lambda. All right, we'll do more examples of this in class, talk a little bit more about the motivation, but I wanted to show you what the process was for figuring out the maximum in this video so that we didn't have to take a lot of time in class to go through this process again. So again, just to recap, remember we created that likelihood function by taking the product of the PDF, plugging in the random sample, and differentiating it with respect to the parameter that we're trying to estimate and maximizing that function. Remember, to get that maximum, ordinarily, since taking derivatives of products is more difficult, we changed it to the log likelihood function and maximize it instead so that we get sums. Like I said, we'll do more of these in class, and I'm going to post a couple of extra videos showing examples of finding these things. But I wanted to give you a taste of what this looks like before we start talking about it in class.